Hello and welcome back to Probability Theory, the video series where we talk a lot about how to deal with randomness. And in today's part 35, we go deeper into the field of statistics and will define so-called point estimators. Moreover, we will also explain what it means when we say that such a point estimator is unbiased. However, as always, before we start with the definition, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget that you can use the link in the description to download a lot of additional material for the videos. For example, you can find books, quizzes and the PDF versions for the videos. Then without further ado, let's immediately start with statistics again by recalling the important definition of a statistical model. Essentially, we just have a collection of a lot of probability spaces where Xn is the sample space as a subset in Rn. And then on the Borel sigma algebra, we have a product measure defined and we call it Pn theta. And indeed, the parameter theta here goes through a whole parameter space capital theta, and this tells us about our gap in knowledge. Therefore, the tools in statistics should give us an estimate on the correct value theta here. So you already see two important steps in statistics. First, we have to choose a suitable statistical model, and then we also have to find suitable estimators. And the information we can work with are the samples from the sample space, where n is the size of the sample. So you can just imagine that we have n measurements of the quantity we want to know. And then the calculations we can do in this model are always with respect to a chosen probability measure p theta. So for example, if we want to calculate an expectation with respect to our p theta n, we would call it E with index theta and superscript n. With that, it's totally clear which probability measure we have chosen. So you see, a lot of things don't change from the standard probability theory we had before, but the interpretations are completely different now. Simply because we want to construct some suitable random variables to extract some information here. And indeed, often our statistical model is not too complicated and theta can be chosen as an interval. And then we simply speak of a one-parameter statistical model. This is quite helpful because then we can use functions, real-valued functions, that map into this interval. And maybe it's really helpful to think of the example we have presented in the last video. There, capital theta was given by the interval from -5 to 5 and p theta by a normal distribution. More precisely, there the variance was fixed by 1, but the expectation of the normal distribution was unknown. Therefore, now the goal for a point estimator would be to find the best fitting theta for this normal distribution. Indeed, this is the simplest version of an estimator because it just gives us one point we can talk about. But before we look at examples, I would say we should write down the formal definition first. So we take a statistical model and let's assume that our theta is given by an interval again. For the moment, this makes everything much simpler and we can look at generalizations later. And now what we do is to look at a chosen random variable. This one we call t, and we usually also put an index n. And then it just maps xn into the parameter space theta. And since in our case theta is an interval, we just have a real-valued random variable here. So nothing special, but this is what we call now a point estimator. The name makes sense because it just estimates a point in our parameter space theta. However, under the hood, by definition, it's just a standard random variable. And you might already see here, the reason we introduce a new name is because of the interpretation. It's a specially constructed random variable with a goal in mind. In order to understand this, it might be really helpful to look at the example from before again. Which means here we have a point estimator for the expectation of the underlying random experiment. And actually, we already know how to get such a nice estimator here. So what we have to do here is to say what happens when we put a sample into Tn. And in our case here, the sample consists of n points, so x1, x2 and so on. And now we already know what we want to get out here is a real number. And now please recall that we have already discussed the sample mean as a statistical quantity. So we just have the sum over the samples divided by n. This is what we usually denote by x bar, and it's a point estimator. So it totally makes sense that this is an estimator for the expectation, but how good it is, we can discuss in the future. Here first we should look at another example where the variance is our parameter. In that case, we get a point estimator for the variance. And also this one, we already know, it's just the sample variance. Which simply means that we have to look at the square deviations from the sample mean. Hence we have xj minus x bar squared. And then as before, we just have the sum from 1 to n. However, now what happens is that we divide this by n minus 1. When you see this factor for the first time, you might be a little bit confused, but we already know this factor makes the whole point estimator unbiased. And now we are ready to actually formulate the definition of a bias. Indeed, often we want to have an unbiased estimator, but I can already tell you, usually we want to have even more. But first, let's start here with the definition of a bias. So as before, we take a point estimator Tn that maps into the real numbers. And this tells us that we can nicely calculate with the thetas as well. So for example, we can fix a theta and then we can calculate the expectation of Tn. So please recall, this means we have the expectation of Tn with respect to the probability measure p theta n. So this is the value we expect from Tn if theta is fixed. So it makes sense that this expectation should be actually the fixed theta. If that's not the case, then this expectation is either bigger or smaller than the given theta. So it's a systematical bias we have in the one or the other direction. More precisely, it's the bias of the point estimator Tn at the given point theta. So at different points from the parameter space, the bias could be different. But it's definitely something we can measure here, and it defines a function as well. So maybe let's call it bias at theta of Tn. And now most importantly, we can define the term unbiased point estimator. And there it's already clear what we want. We want to have a bias is equal to 0 for all points theta in the parameter space. So the bias function is just equal to 0 for all theta. And now you know that we already have examples for unbiased point estimators, namely the two above. However, the proof for this and some discussions for some other examples we can put into the next video. Hence, I really hope we meet there again and have a nice day. Bye bye.